So this is our topic for today. Relations, functions, and the graphs of those relations and functions. Right? And if you were, if you've been to high school and you were exposed to any kind of high school mathematics, you would have been exposed to what we call a relation. Maybe if you, I mean, wrote CXC and so talked about functions and were introduced to the graphs of various types of functions. So the first thing we want to look at, and this is more of a review, right? Let me see if I can make it small enough to fit everything on the screen. Yeah. We just want to review a little definition of what a relation is. And in mathematics, you'll see them defining a relation as a set of ordered pairs. And we got a little example there, right? Right away, mention is made that it's a set. So therefore, you'd have to put a curly brackets. And then within the set now, each member is basically an ordered pair. As you see here, we annotate. As you see here, this is a pair, that's a pair. So the set is made up of these pairs, right? So each of this is a member of the set, right? Each pair is a member of the set. And why they call it a relation, you can see that there's some kind of relationship between the first and second number. Look at it good. Can anybody say? Can you see the relationship? Look here. 0 and 2, 1 and 3, 2 and 4, and so on.
Odd and even numbers, sir?
Odd and even? No, look, 0 is odd or even.
No, I meant set of even numbers, set of odd numbers.
No,
and so
no,
forth.
no, 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 no. Look at each pair. Look at 0 and 2, 1 and 3, 2 and 4. Do you see a relationship between the first number and the second number? The first number and the second number. Do you see that?
Yes, sir.
What is see happening? What do you see happening?
I think the zero, it's skipping every other number.
How do you say that mathematically?
Continent tools, sir.
All right, you close there, right? You take, to get the second number, you add 2 to the first one, right? So you add 2 to 0, you get 2. Add 2 to 1, you get 3. You add 2 to 4, you add 2 to 2, you get 4. Add 2 to 3, you get 5, and so on, right? So there's some kind of relationship between the two numbers in each pair. And that's why they call the thing a relation. It's not just random numbers, but there's a relationship between the numbers in each pair. Right? And we'll get into a lot of examples and different types of relationships and so on. But there's a name we give to the first, all these first numbers. If you were to put them in one set, right? We were to put them in one set, and we call it the domain, right? So this the relation, we call it R. It doesn't have to be R, it can be all kinds of letters, right? A set you usually denote by a capital letter. I just use R because I think of relation starting with R, so I use R. But you don't have to use that. You can use all kinds of letters, especially when you're going to deal with several types of relations, right? Or several relations you're dealing with. You have to find a different letter. Every time you can call all them R, right? Good. But what I'm doing now, I'm extracting the first number in each pair. And these are the numbers here, right? And there's a name for that, right? that set is called the domain of R. The domain. And later on, you're going to learn that that is the input. You put in that number, right? And you get out what we call the range, right? So in this relation, you put in 0, you get out 2. You put in 1, you get out 3. Put in 2, you get out 4. Put in 3, you get out 5. Put in 4, you get out 6. So what you put in, that set that you put in is called the domain. What you get out is called the range. Clear? Now there's another
Yes,
term
madam.
that is used when it comes to relations, functions, and graphs. And that's something called the codomain, right? And usually the codomain sometimes is defined as a bigger set that the range would fall into. The range can either be equal to the codomain, but at times the range can be just a smaller subset of the codomain, right? Let's keep that in mind. You'll understand that if you do some higher mathematics and so. But for now, you just keep those terms in mind. The domain is really the input. It's the force number of each pair, right? That the collection of all of them makes up the domain. The range is the output, or the second number in each pair. And as we're saying now, that the codomain is like a big set that contains the entire range of this relation. I think I have to erase all of this, so I don't see what will remain there on the. I think so. I can just throw away this file. All right, good. So now what we want to do is we want to learn how to represent relations. We just talked about it can be represented as a set, and that's what you see here. That's what you see here, right? So you can use set notation and do it. Yeah, all well and good. And more to what we were doing for a couple of weeks now, this matter of algebra, right? We can write it using algebra now, right? And this is how we read this. X is such that X maps onto X plus 2, right? So X is like the input and the output is X plus 2. And you can see that, right? 0 being the input or the X value for this pair, X plus 2, which is 2, is the output, right? So this is the input. That's the input. That's the output, right? So the relation is defined as X is such that, that's what this colon means, right? X maps onto X plus 2. So we got set notation. Now we have an algebraic representation involving X, right? Where you can define what the input is and what the output is. For those who go on to study computer science, you know, this kind of thing will show up again and be very, very useful to you. Right? For other people, they hardly make use of this kind of thing. Another way to represent relations is what we call a mapping, or sometimes you hear the books say arrow diagram, right? So we have the domain in a loop there, right? And we have the range in a loop. So 0 maps onto 2, 1 maps onto 3, and so on. And because you're seeing that, okay, this one of this maps onto one of that, right? And you're seeing that pattern recurring over and over. We call this a one-to-one relation, a one-to-one relation, right? You know, let me say 1, 2, 1 relation. Follow so far? Another way of representing that same relation is by a graph, right? And remember the relation, the points were okay. This point is 0, 2. Oh my, supposed to be a comma. 0, 2, 1, 3, 2, 4, 3, 5, and 4, 6. Can you see how we plot those points? This graph down here, you call this the x-axis, right? And this axis, usually we call it the y-axis, right? The y-axis. But we haven't reached there, right? We haven't reached there. So for now, we call this, okay, the x-axis. We'll call this the x plus 2, right? Axis. Let's say that for now, right? Or this is the input. Let me write, I think this is a better description. Input and say output, right? The output is on the vertical axis. The input is on the horizontal axis. Later on, you'll see why we're calling this the y-axis, and then so there you'll see us using a relation, something called function notation. We'll call it the fx axis. We'll come to that. But I want you to see how we plot like the point 0, 2, 1, 3. So 0 on the input axis or the x-axis. So anywhere here, anywhere along here, x is 0, right? And y or the output is 2 anywhere here. And notice the 2 coincide there. So we call that point 0, 2. Similarly, anywhere here, x is 1. I know I'm not drawing very straight. And anywhere here, the output is 3 or y is 3. So the 2 intersect there. And where they intersect, that's the point, 1, 3. Are you following how to plot a graph or how to read off a point from a graph?
Yes, sir.
Everybody
sir.
Yes,
follow that?
sir.
That's a very
Yes, sir.
important skill,
Yes,
right?
sir. Yes, sir.
Especially, I mean, regardless of what you study in the future, if you can't read graphs and charts and diagrams and drawings, you can hardly make it in this life, right? Everything now is pictures and drawings, and people hardly write these days. If you study statistics, oh my, right? If you get into management sciences and so, right, you'll have to do a lot of mathematics in the area of management, right? Because management is a lot of mathematics, right? I don't know if anybody will, a lot of people will get into those things. Economics, anybody interested in those areas? Economics, management, accounting.
Yes, sir.
Yeah, those areas. If you can't read and interpret a graph, you can't draw a graph. I know these days you have powerful tools that could do it for you, which is a good thing, and you're free to use those, right? As a matter of fact, you wouldn't go on, let's say you're pitching to your boss some idea, and maybe you want to show them some figures. You do some market research and how many people buy the thing in January, how many buy it in February, how many buy it in March. You just can't tell people numbers like that. People like to see it, see a picture of it, and if you can put together a nice little graph, a bar graph or a line graph, like this is really a line graph you're seeing here because it's a line. Right? If you can do that, right? You learn all kinds of things. We'll touch on a bit, just a bit in this course at the end. It's going to be very useful. So, understanding graphs, plotting them, even if you don't have to plot them by hand and you have to, the computer does it for you. It's good for you to understand what you're seeing, right? Read them, interpret them, right? I was doing a course. The course was business mathematics. And I was showing the students how they have this thing online where people would, well, the version that is available in Guyana is a lot like gambling. But in America, they have real places that you can go and buy shares and stocks and so, right, of companies, right? And you are guessing or you are looking at the behavior of the stock, right, or the shares, and see how if it's going up or coming down. And you have to be able to interpret those things, or else, you know, um, you're in big trouble if you make investment and the thing doesn't work. I think I should pause to show you those charts, just out of interest, right? Let me stop sharing for a moment. Let me pause the recording. I want to find the chart just to show you something. Yeah. So back to our graphs, right? So this is another example. I have another relation here. -2, 4, -1, 1, 0, 0, 1, 1, 2, 4. Right? I don't know if you can see it. Can you see what's happening to the number? What do you do to -2 to get 4? What do you do to -1 to get 1? And so on. What do you see happening? Anybody? I mean, it's staring you in the face here. If you take -2 and you square it, you get 4. You take -1 and you square it, you get 1. 0 you square it, you get 0. 1 you square it, you get 1. 2 you square it, you get 4, right? So that's the relationship in each pair there. One is the square of the other, right? Algebraically, this is how you write it. X is such that X maps onto X squared. Right? That's how you write that. And then this is how the mapping diagram look, or the arrow diagram. And because there are some cases where you see like, okay, -2 and 2 goes to 4. Similarly, -1 and 1 go to 1. Because you have more than 1 going to 1 in some situations, we call it a many-to-one. A many-to-one relation, right? A many-to-one relation. Follow it so far?
Yes, sir.
And this is what the graph
Yes, sir.
looks like, right? This is what the graph looks like. Again, you put the input here, the input. I'm not going to call it X yet. And this is your output, right? So you got what? -2, 4. So here is -1, 1. This part is the origin, 0, 0. Down here is 1, 1. And here is 2, 4, right? Very important, to draw a graph, read a graph, This is a third one, right? So this might be harder for you to figure out. So these pairs here, do you see that the first number, if you take the square root of it, you get a second one, watch. square root of 1, you get minus 1, as well as 1, 2, right? Square root of 4, you get minus 2 and 3. Square root of 9, you get minus 3 and 3, right? Good. So we take all of that. This is how we represent it. X is such that X maps onto the positive and negative square root of X. And on the mapping diagram, you see sometimes 2 arrows leaving some of these elements in the domain. Because of that, we call it a one-to-many relation. One-to-many relation, right? Because you're seeing 1 to more than 1. 1 to more than 1. 1 to more than 1. I mean, this is an exceptional one. You call it a one-to-many relation. And that's what the graph would look like, right? So, like, okay, I think what we had. 0, yeah, 0, 0. And you got 1, 1, as well as 1 minus 1, and so on, right? What was it, 4? At 4, 2, as well as 4 minus 2, you know, and so on. So now we turn our attention to a special type of relation. The relation is called a function. So when is a relation a function? Well, here's a definition that I mean, when you look at it, it might be difficult for you to grasp until you see examples and so, right? So it says here that a relation is a function if for each element of the domain, there is one and only one element of the codomain. That is very difficult to picture, right? But this is a better way of, or I think a more understandable way of defining it, right? One-to-one relations and many-to-one relations are functions, right? Because if you were to take, let me take the one-to-one. Let me go to one-to-one. So you got something here. And what they're saying, for each element of the domain, it matches to only one over here. You don't have it going to 2. No. It only goes to 1. In other words, 1 arrow leaves every one of these. Right? 1 arrow leaves every one of them in the domain. And then you call it a function. So now the F comes in. Right? The F comes in that if a relation is a function, you use this F notation, right? So you say a function is such that it maps the real numbers onto the real numbers. I know at CXC they usually don't do this. They don't tell you that, you know what, the domain of the function and the codomain of the function is this and that. No, they don't usually tell you. You usually assume. I think you don't even assume, you don't even conscious that when you define a function, you're supposed to spell out what's the domain, what's the codomain, right? But usually the teacher don't tell you nothing. The teacher just give you a function and you take it and you do all kinds of things with it, right? For example, like you have the function of x, right, is such that x maps onto x plus 2. Right? Function of x is such that x maps onto x plus 2. Right? The domain of this function, in other words, what values x can take on? X can be all the real numbers, any and all the real numbers. The codomain also, all the real numbers. All y is an element of R. And the range happens to be all the real numbers as well. Right? So in this case, the codomain and the range is the same thing. These are very basic ideas in function, right? Unless you study functions to a higher level, you wouldn't have to worry too much about these deeper things. Another example, you're saying that G maps R to R, right? And we're not going to write it with that arrow and so anymore. We'll say Gx is equals to x squared, right? So the function G takes x, right, as an input and would output for these values of x that you input, the square of it, right? So in this case, again, your domain is all the real numbers. X can take on all the real numbers. The codomain happens to be all the real numbers. And in this case, the range is y. We're going to call the values of the range y, right? It's greater than or equal to 0. In this case, the range is not equal to the codomain, right? The reason why I say this is that if you were to plot this graph looks like this. And when you talk about the range, you really mean what are the possible outputs that you can get from this function? You can't get -1 because the graph comes here and turn back right here and go back. You can't get -2, right? So your range is from 0 and greater, not lesser. So while the codomain include -1, -2, -1.5, -10, the range is from 0 and greater, right? That's how you write it. Y is greater than or equal to 0. Well, leave this one for, this one is a little more technical, right? They use the function fx equal 1 over x, right? In this case, x can't be equal to 0. So we have to find some way of saying it, right? So we can say that fx equal 1 over x for all x is not 0. So x can take any value in this whole wide world, any real value that is, except 0. And that's one way of writing it. And this is an alternative way of writing it, right? And your domain, all non-zero numbers. All non-zero numbers that are real. Your codomain, yes, you can say all y is an element of R, all the real numbers. But a range, y must not be equal to 0. It can be any other number but 0. And why I say that, if you know this graph, anybody know this graph? It looks like this. The graph looks like this. Right? So you can't put in x equals 0, right? Remember, this is the x-axis. Okay, we can now call it the x-axis. And this axis is the fx axis. Sometimes we simplify it and say the y-axis, right? You see, we say fx axis or the y-axis, right? And you can see that, well, x can't be 0. The graph doesn't exist here. This is the graph here. This is the graph. These two lines, this horizontal line and vertical line, those are the axes. That's not the graph. The graph is this curve here, right? This curve here. And when x equals 0, the graph doesn't exist. There's a break in the graph. Similarly, y can't be 0 either. There's no value. I can't put no value for x here that will give me 0, right? So while I can't put 0 here, I also can't put a value for x equals 0. No, there's no value of x that will churn out, or the output of this function is 0. And that's why, again, there's a break on the graph here. Graph comes down, but never touches the x-axis. And later on, if you ever study mathematics to a higher level, you're going to hear about something called asymptotes, right? Asymptote. The x-axis and the y-axis are asymptotes of this function. Good. So with functions, we can combine them, right? We're not going to spend so much time on this. We can add two functions, we can subtract two functions, we can multiply two functions, we can divide two functions, right? We can do all of that. And these are some examples here. You have a function, have another one, right? We can add them, just add them up like you do algebra. Add them up, watch. Add these two, you get that. Subtract them, you get that. Multiply them, you get that. Right? Divide them, you get that. Right? So you can do all those operations with a function. Right? Watch them good. I leave them for a while and you watch them good. You see that? Watch. Add these two up. So there is no other x squared term other than this one, right? So you put it back here. But then you got 3x here and 2x. So we add those two, we get 5x. And then we got 2 minus 1, that gives us 1. We finish here. And then you can subtract, and you will get that. You can multiply this out, right? Using the distributive law. That's kind of hard for most of you. So what you do, you multiply this by everything there. So you put 2x times 2 plus 3x minus x squared, right? Minus 1 times, and you write back, I think the space is too limited. Let me do it at the bottom. 2x into 2 plus 3x minus x squared minus 1 times 2 plus 3x minus x squared, right? And you remove the bracket now. So you get, sorry, this will be 4x. Then you'll get 6x squared, and you'll get minus 2x cubed. Removing here, you get minus 2, minus 3x, positive x squared. When you simplify all of this, you are going to get that, right? So when you're watching back the video, pause it and see how they get that, right? Because you can see what this term, look, it's here, right? 6x squared, and this one here, this x squared here, becomes 7x squared. We got 4x minus 3x will give you just x, and then you're left with just this minus 2 here. See that? So that's some algebra there with functions. You can add them, you can subtract them, you can multiply them, you can divide them. There is another useful thing you can do with functions. And it's called function composition. I'm thinking whether I should give you a break now. Should I finish function composition, then give you a break, or you want a break now?
Finish it, sir.
All right, let me not finish this. We'll take a short break and then we come back and do the last thing, right? All right, good. So what's function composition really? I mean, you see it in the real world these days, eh? Long ago, you had a camera, just take pictures. You had a telephone, making phone calls, making and receiving phone calls, right? Long ago, you had a printer, all it does is print. We had a scanner separate. Now you got a cell phone doing everything. Tells time, it takes a picture, it makes calls, it receives calls, serves the internet. That's a classic example of the real world where one device, one machine does so many things, right? Well, function composition is like that. Whether you can, you might have two functions doing different things. Could you combine these functions to have a third one, a composite, that will do the work of both of the individual functions? Yes, you can do that. And that's what this is saying. The composite of f and g. In other words, what they're saying that if you take an input and you perform g on it first, gx on it first, and you take the output of gx and put it into fx, what will you get? That's basically what they're saying here, right? It's a composite of f and g. Composite of f and g meaning the fact that g is on the inside means g is done first. That function is done first. And the output of the inner function, you put into the outer function. In this case, f being this side, f being on the inside, you perform f first, and the output of that you put into g, the outer function. And that's what you see here. You find fx first, whatever the answer is, then you put it in g, right? Function composition. And we're going to see some examples here. So we got two functions, right? Fx is 2 plus 3x minus x squared, and gx is 2x minus 1, right? So this means you multiply the two, right? We're not going to deal with that. The multiplication, that's it here, right? We multiply the two. We're not going to deal with that, right? We're not going to deal with that. We're going to find the composite of f and g and the composite of g and f. And it's interesting to see whether they're the same thing. So f and g, well, here, right? All right. Yeah. The composite of f and g. So we're taking g, which is 2x minus 1, and we're treating it like, we're treating this like a x, like a big X, So we're putting the whole of gx in the place of x here and here, right? And that's what you see here. So we got 2, we put value 2. 3 times, we're not putting just x now, we're putting the whole gx minus gx is 2x minus 1 squared, right? So instead of this x, we put in the whole of gx, which is 2x minus 1. Well, now we have a lot of work to do. We have to use the distributive law, remove the bracket, again, use the distributive law and do this square, right? And when we finish, simplify and we get that, right? For those who don't know how to do this part, I think this will puzzle people. Let me write it here. 2x minus 1 square is equivalent to this. 2x minus 1 times 2x minus 1, right? And I'll show you a shortcut how to do it. You can use the distributive law, you can do this. 2 by 2x, and then 2x by 2x, and then 2x by minus 1. So you get 4x squared minus 2x, and then this minus 1 by 2x, which is minus 2x, this minus 1 by minus 1, you get positive. End up with 4x squared. This 2 becomes minus 4x plus 1, right? And that's how they got that in. And then you simplify. Now, that's the composite of f and g. In other words, you're putting gx inside of fx. Now we're looking at the composite of g and f, which means you're putting fx wherever you see x in g. So we're taking this whole thing now, and we're putting it in the place of this x, right? We're doing that. And then we're removing the bracket. And you get that. And do you notice that this is not the same as that? Right? It's not the same as that. So function composition is not commutative. Right? The composite of G and F is not the same as the composite of F and G. And I try to illustrate it here, right? So if I take gx, I take the number 0 and 1, put it in gx, the output is going to be minus 1, 1. If I take this now and put it in fx as the input, I get out minus 2, 4, minus 2, 4. Right? So I did two functions here. However, if I take this input and I put it in the composite of f and g, right? I will get this output, which is that here. So this one function does the job of these two together. Right? That's the whole idea of function composition. Good. So we're gonna stop there for a little. Take a few minutes, right? How long? 50 minutes?
All right,
Yes,
sir.
sir.
Let me pause this recording. Good. So the final thing we'll look at when it comes to functions is something called the inverse of a function. Right, we talked just now about a composite where you can find a single function that can do the work of two functions. You can have the composite of 3 functions and so on, right? Now we want to talk about a function that can reverse the operation of an original function. Right? So here we have, okay, watch this. We have 2 functions. We got fx is this, and we got gx is this, right? So what we see happening here, we put in minus 1 in f, and you get out minus 5. Right? If you were to take minus 5 now and put it in g, we get back minus 1. Look at this. F took 1 and get minus 5. G took minus 5 and get out back minus 1. So it looks like G is doing the reverse of what F is doing. Right? It's undoing the effects of F. Right? Similarly, look here. We take 2, we put it in G, we get 4 over 3. If we take 4 over 3 and put it in F, we get back 2. So what we see happening is that F and G seem to be kind of working against one another in that one reverses the operation of the other. And when that is the case, when one function reverses the effects or the operation of another function, we call them inverses of one another. One is the inverse of the other, right? So that's the whole idea of the inverse of a function. So look here. Same thing we do in calculations, we do it on a graph here, right? On like a mapping diagram. So if you were to take these two numbers, put them in the function f, it will churn out these. If you were to take these instead and pass them into G, G will churn out these, right? So they seem to be working against one another. What one does, the other one undo it, right? And that's what inverse functions do. Good. Skip this a little. I want to go to the process. How do you find the inverse of a function? Right? How do you find the inverse of a function? Well, this is what we do. We take the function, we let it be equal to y, right? So you just make that substitution, right? Then what you do, you kind of interchange x and y in the function up here. Your next step is to make back y the subject, right? And whatever expression you end up with, you name it f inverse x. And the result that you have is the inverse of the original function. I'll demonstrate this process with examples later on. Don't worry, right? This is an example. So you have the function fx equal 3x minus 2. And then you are told find the inverse of x, right? So what did they say we do? First, we instead of fx here, put y. So that's what we did here, right? So this whole thing becomes that. Next, we kind of interchange x and y. That's what happens here. And then now we make back y the subject, right? And remember I talked about transposition the last day. Transpose to make y the subject. So we take the 2 over, that's what we did here. And then we take this 3 over and divide everything. So you can leave it like this or you can write it like this. And now the inverse, this is how you write it. F, you put a minus 1 on top there, x. F inverse x equal x over 3 plus 2 over 3. Right? You can also write it like this. So you can write it how they have it here. 1/3 x plus 2. You can do that. That's not a problem. Same thing. You think you follow the process at all?
Yeah, following.
Okay. Good. Now this one looks a little, it's more of an application of inverses, right? So here we have a function, hx, right? And it's given by this function here. And they're telling you, find h inverse, right? We just went through how we can find an inverse of a function. It's just that this one looks harder, right? So leave it for now. We're gonna find it. However, they tell you, and hence solve this equation, right? Solve this equation. Why are they telling you that this inverse can somehow solve the equation? But if you watch, this part of the equation is really hx. So what they're telling you is that there's some value x that you will put into hx that will give you an output of 7. But remember, the inverse of a function will take this output and lead you back to x. Right? Remember, the inverse reverses the operation of the original function. So if you take 7 and put it inside H inverse, the value is going to be X. Right? And that's what they did here and get 3. But we'll come to that. Let's find the inverse before we go any further. So we're gonna go through the steps again. You let Hx be y, so you put back the function there. So y is equals to, put back the function. Then you swap around x and y, right? Where you see x, you put y. Where you see y, you put x. So we have this now. Right? That shouldn't be difficult for you. Your next step now is to make y the subject. Trouble with it is that there's a y here and there's a y here. And I think I did do an example. I don't know if you're watching the videos back afterwards. I did an example where you have 2 of the variables on one side and you have to somehow bring them together, right? So we cross multiply and we get this, right? Do you see that? It's like you put this over 1, multiply that by that, and that by that, and you end up with this. Remove the bracket, right? And what we do now, try to get all the y's to one side and everything else the other side. So we take this y, bring it over here, and take this minus 5x over there. And this is what we get. 2xy, this y goes over, become minus y. This minus 5x comes over here, becomes plus 5x. So all the y's are on one side, right? We now factorize out the y because y is common, right? Y is common, so we factorize out the y and we get 2x minus 1 times y equal this here. And then we bring down this and we divide over here and we get that. So we have just found H inverse, right? We have just found H inverse here, right? So we have H inverse x equal to that. So as we said, this inverse can now take 7 and churn out the value of x, right? So we take the 7, H inverse 7 is equals to x, and we put the 7 in H inverse, this here. And we get x equal 3. And that's our solution. You can try it and see. 3 plus 4, 7. 7 over 2 times 3 is 6. 6 minus 5 is 1. So 7 over 1 equals 7. It's a simple application of the inverse of a function. I mean, if you have to solve such an equation, you wouldn't have done it this way, but it's just an alternative way of solving an equation, making use of what we call the inverse of a function. And there's one little bit here. It's an interesting fact that if you take a function and its inverse, you will see that their graphs is a reflection of one another in the line y equal x. It's just a miracle of mathematics, right? Gx and its inverse, they're both a reflection of themselves in the line y equal x, right? That's what you're seeing here. Any function. If you find the function and you find its inverse, the two of them will be a reflection of one another in the line y equal x. Right? And we can actually we can show that at any time. Maybe what I can do, let me stop share for a brief moment, or let me see if you all can, let's go with Desmos, just to demonstrate maybe 1 or 2. Everybody can see this? You can see a graphy looking thing?
Yes,
Yes,
sir.
sir.
All right.
Yes, sir.
So let's take a function. Y equal 2x minus 1. That's a function there, right? Let me go with well, I'm trying to get a number that would really show. Let me go with 1/2. Let's go with that. And I'm going to go with y equal. Remember, I have to use y, right? I can't use inverse. So what will this be? 2 brackets. Right? So this is the inverse. Well, you can figure that out, right? This is the function, this is its inverse. And finally, we're going to put a line y equal x. Right? And what do you see? So this red one is the line y equal half x minus 2. This blue line is the line y equal 2 bracket x plus 2, which is the inverse. This here is the inverse of that. You can jot it down and see if you can prove by yourself, you know. Find the inverse of half x minus 2 and see if it's not this. Right? And you can see from the looks of it, if you watch this here, the whole setup here, you're seeing that this red line is a reflection of this blue line in this green line. Think of this green line like a mirror. You know this green line here? It's like a mirror. So this is reflected in there, right? See it? You see it? Doesn't it look like the reflection of one another?
Yes, sir.
Yeah, right? It's just one of those miracles of, you know, geometry and mathematics as a whole. Right? All right. So we covered everything there on functions that we need to touch on, right? So I'm going to stop with the recording here.